Hello everyone, welcome to lecture 21 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture is on applications of LSPR. So here is the lecture outline. We will see how LSPR is used for scattering, and we can use nanoantennas for different, or nanoparticles as nanoantennas for different wavelengths. We will also see the effect of substrate on LSPR. We will see the application of LSPR in nanosheets. We will look into surface enhanced Raman scattering, as well as we will also look into the applications of LSPR in fluorescence enhancement and in tunable optical devices. So, we have seen this diagram before, that nanoparticles, they scatter light very strongly when they are at resonance. So, here the different colors of nanoparticles depending on their size. Now, if you see the gold nanoparticles, when the size ranges from 20 to 150 nanometer, that is the diameter, the resonance wavelength changes from 520 to 660 nanometer. For silver nanoparticles of similar size, the resonance starts from 380 nanometer to 600 nanometer. Now, how you can calculate that at what size of the particle, what is the resonant wavelength? You can actually look into this formula that we obtained in the previous lectures. You can find out what is the scattering cross section, how you can calculate it from alpha, which is the polarizability of this tiny particle. So, this is the polarizability. When you put it here, this is the expression. Similarly, you can also find out what is absorption cross section, which is calculated as k imaginary part of alpha, and this is what you can get. Okay. So, overall extinction cross section will be given as scattering plus absorption cross section. Now, the applications of nanoparticles and LSPR, that ranges from nanoscale devices and circuits. These can be used for switching applications based on nanoparticles. They can be used as absorbers in plasmonic solar cells. You can also use nanoparticles as absorbers. As I mentioned previously, you can inject gold nanoparticles with some biomarkers, so that they can go and deposit on the tumor cell for a cancerous patient. And when you shine infrared light through the human skin, infrared light can penetrate and go and get absorbed by those nanoparticles, and there will be heat generated, and that will allow the tumors to get killed by thermal ablation. You can also use them for biological and chemical sensing. So, in the presence of nanoparticles, the near field gets enhanced. So, that also allows the enhancement in biological and chemical signatures or footprints of any molecules or biological species. They can also be used for optical data storage. Now, nanoparticles gives you sub-wavelength control of electromagnetic radiation, so that can help you have much more denser optical data storage. You can use this force on single atoms to drag them somewhere in the near field. So, you can use them as optical tweezer. They can be used as directional nanoantennas, what we have seen in the previous lecture. You can also use them for maskless fabrication technology. Like if you have to make a metallic wire, you instead of using mask, you can line up nanoparticles and then you shine light, and those nanoparticles at resonance will absorb that light, get heated up, and they will melt, and that will give rise to a wire. Okay. So, that is maskless fabrication technology. Okay. Now, let us look into some details of LSPR right now. So, let us study the effect of nanoparticle size. In the previous lecture, I told that surface scattering of oscillating electrons, okay, that actually changes the line shape of the plasmon resonance. So, the plasmon line shape gamma broadens with 1 over r. So, if you remember the expression of polarizability, you can also see that how this polarizability depends on this gamma, which is the damping constant of the metal nanoparticle. So, if you write down the permittivity of the metal like this, 1 minus omega p square over omega square plus I omega gamma. Gamma is the damping constant. Here it is shown that as gamma increases, the resonance get shorter, means weaker and broader, okay, and the broader is also associated with the damping directly. Now, when the nanoparticle size is smaller than the mean free path of electron in that particular metal, then there will be some additional scattering losses, which is surface scattering, as it is shown here that gamma is basically inversely proportional to R. So, that is also seen here, that this gamma will be now replaced by this new gamma, which is this small gamma. Small gamma is this capital gamma naught, they are the same thing. A Vf over R, A is a constant, usually it is taken as 1, Vf is the Fermi velocity of electrons and R is the radius of that nanoparticle. Now, on the other side, this is when the particles are too small than the mean free path of the electrons, you get additional scattering loss, there will be broadening in the spectra and the resonance becomes weaker. On the other side, when quasi-static approximation breaks, when the particle becomes too large, greater than 100 nanometer. In such cases, there are additional effects. We have also seen that alpha gets now additional terms coming from redshift, which is due to the retardation, and also there are broadening due to radiative decay, and you can see both of them here, that this is for silver nanosphere. As you keep on increasing the size of the silver nanosphere from 20 to 40 to 60 to 80, you see you are getting a red shift because the resonance is moving towards longer wavelength or red side, okay, and they are also getting broadened. So, the broadening is because of this radiative decay, and redshift in the larger particle is because of the retardation. Now, what is this retardation? In quasi-static theory, if you remember, we assume that the phase on top of a particle does not change because the tiny particle is very tiny as compared to the wavelength of light. But when the particle size increases and it becomes comparable, or it becomes pretty large, comparable in the sense like it's like lambda by 4, lambda by 5, something like that, okay. In that case, you will see that over the surface of the particle there are some phase changes, and that will not allow all the electrons to oscillate in sync or phase. So, that will cause the broadening and the redshift. So, these are the reason behind these two effects. Also, higher order resonances will come into picture, like if you see, if you further increase the size of the silver nanosphere from 100, 120, 140, 160, 180, 200 and 300, you see that the dipolar peak is getting weaker and weaker. It is getting redshifted, no doubt, but it is getting weaker because new resonances are coming up. Because here you see for 80 there was a small shoulder. So, this was a higher energy peak, shorter wavelength means higher energy. So, here also you can see that particular case, that you are able to see that this is the dipolar peak, and at higher energy you are getting another peak, and with larger particles both higher energy and the dipolar peak are actually getting redshifted. So, this one got shifted here, this one got shifted here, further increase, this got shifted here. So, they are all red shifting, and that at 140 you see another shoulder is coming up, and 160 you got another peak. So, dipolar, then the next mode comes into picture is octopolar, then the next mode comes into picture is dipolar, quadrupolar and octopolar, 2, 4 and 8, okay, and so on. So, with that you understood that it is possible to have different plasmon resonance with a single particle sphere, say or single material sphere like gold nanosphere or silver nanosphere, but the resonance strength weakens and it also becomes too much broad. So, that is not a very strong resonance. So, you can look into this particular chart, and that will help you about the tunability of localized surface plasmon resonance. So, silver nanospheres scatter from 380 to around 600 as we discussed. So, gold nanospheres starting from say 520 to 660 as we discussed before. But look at this nano shells or nano eggs, they have very wide range of tunability, starting from visible range to mid infrared you can tune with them. Similarly, nanorods, triangles, cubes, nano rice, these are different shapes of the plasmonic nano antenna which allows you to achieve plasmon resonance at different wavelength, and this is the tuning range, means just by changing the size of the particle you can go from this wavelength to this wavelength or this to this for nanorods. So, that is a huge kind of tunability. Now, let us look into the mathematical derivation of how nanoshell or core shell nanoparticles, okay, they give this tunability. So, if you consider a core shell nanoparticles, so this is how it looks like, this is the core and this is the shell. So, the core radius is R1, the overall radius is R2. So, what is the shell thickness? R2 minus R1. So, this material, the core material is epsilon 1, shell material is epsilon 2 and the outside surrounding media is epsilon 3. Now, in quasi-static theory we have to remember certain things, that the particle diameter, so R2 or diameter, so it is 2R2 should be much smaller than the wavelength of light. Then the incident field is time dependent, but it does not vary spatially on the particle. So, that is what quasi-static, okay. And in that case you can actually use electrostatic solution by solving the Laplace equation for potential. So, this is how you can define the potential phi. So, Ai and Bi are the two constants which correspond to monopole and dipole terms. So, this is the general formula. I means you can put I equals 1, 2, 3. So, that will be the generic equation of potential in the 3 region. Now, what next? You have to apply the boundary conditions at the core, shell and the embedding medium boundary to see and to find out what are these constants A1, A2, B1, B2 or A3, B3 and so on. Okay. Now, what are the boundary conditions? Always remember it has to be the continuity of the tangential component of the electric field. So, if you write that, this is how you write it. So, at different layers this is how the tangential component should be continuous. Now, with that if you put the second condition, which is the normal component of the displacement field. So, normal component is, so dou E, dou phi by dou R is basically electric field, and when you multiply with epsilon, that is the permittivity, this gives you D, okay, that is the displacement field. The displacement fields are also continuous, the normal components. So, normal components you can find out by taking the derivative with respect to R, okay, what is normal, and the tangential one you can find with respect to theta, that is shown here. So, once you do that you can put, there is no monopole here. So, the term A1 goes to 0, only dipole will be formed. So, you can also find out what is, there is no electric charge at the center. So, you can put B1 also equals to 0. In the outer region, in the space, okay, far away from the particle, the potential phi 3 is minus E naught R cos theta. E naught is the incident electric field. So, that also tells you that A3 is nothing but minus E naught. So, A3 and B1 you have determined, okay, and you can put it back into the previous equations and solve it to find out what is A1, A2, B1, B2, okay. So, once you do that you can obtain the potential phi. I am not going into the derivation, that's easy, but it is bit lengthy. So, once you know that, you can always find out what is E1, E2 and E3, that are the 3 different electric fields. So, these are the expressions. You do the calculation or you can plot it using some kind of programming software like MATLAB or Python, you will be able to get these equations, okay. And then finally, you will find out the electric field in the third region, that is E3. So, there you can see that you are actually having some components like EA, that is dependent on epsilon 1 and epsilon 2, and also P. P is nothing but the volume fraction. So, it is the ratio of the shell volume to the overall partial volume. So, this is the parameter that brings into the ratio of shell and overall particle volume into the picture. Okay. So, epsilon A, epsilon B are the two new terms which are nothing but this. So, these are basically some kind of simplification in the formula. Overall, how we do that, the polarizability of a equivalent dipole of this core shell nanoparticle will be given as epsilon 3 alpha E induced. So, you can, from that you can find out what is the alpha, that is the overall polarizability that is induced by this particle, and this is the form. Okay. So, 4 pi epsilon naught R2 cube, and this is the equation. I am not going through it details, but you can compare this with the nanosphere and you will be able to see the difference. And here epsilon 2, epsilon 3 and epsilon 1. Where is epsilon 1 in this? That is actually inside epsilon A and B. Okay. So, with this you can find out what is your alpha. Once you know alpha, it is very straightforward, you can obtain the scattering cross section. So, sigma is the cross section. So, sigma scattering is 1 over 6 pi epsilon naught square k to the power 4 modulus alpha square. You put this, you get this particular formula. Okay. So, here one thing you can remember that n, that is a refractive index, outside can be taken as square root of epsilon 3, because this surrounding media is a dielectric. So, you can simply take this one, not a problem. Similarly, you can obtain what is the absorption cross section, that is basically k over epsilon naught imaginary of alpha. This gives you the, once you put alpha you get this expression. So, overall you will be able to find out the case. Now, using this you can find out the total cross section. If now let us take one example of gold coated gold sulfide nanoshell. It means the core is basically gold sulfide and it is coated by gold. Okay. So, if you take that kind of a particle with 2 nanometer shell thickness, okay, look at this figure. This figure shows the calculation of the total cross section. So, it is basically summation of scattering cross section and absorption cross section, and this is a gold coated A2S nanoshell. So, gold is the core and you have gold sulfide on the outer shell, okay, and the shell thickness is 2 nanometer, and in these 3 cases, okay, R2 has been changed from 4, 10 and 17. So, you can see as the overall size of the particle becomes larger, you get a redshift and the resonance also gets stronger, okay, and these circles that you see, they are basically from the quasi-static theory calculation, and the solid line is from the generalized Mie scattering theory. So, we have seen the Mie scattering theory possible for nanospheres, they are also possible for core shell nanoparticles, and you see that the quasi-static theory is very close to the Mie scattering theory. It means for this size of particles, okay, quasi-static theory is a very good approximation. Fine. So, if someone tells you, okay, this is the polarizability alpha, what is the condition for resonance? The condition for resonance is that when the denominator, the real part of the denominator goes to 0. So, you can write real of this going to 0. So, you can actually find out what is that. So, you put epsilon A and epsilon B into this equation, you can find out the condition R1 by R2 equals this. So, this is the condition for resonance. So, you again take that example of gold coated AU2S nanoshells, okay, and in that case you can see R core, which is basically R1 divided by R total, that is basically R2 is this one. So, you can change this ratio from 0.62 or something or 61 to 0.9, only this much variation, you are able to change the resonance wavelength from 600 to 1000. Now, you can correlate with that kind of large span of nanoshell that I have shown previously, that it is possible to get a huge tunability by going to this kind of core shell nanoparticles, where a metallic core is coated with a nanoshell, okay, and this also can be done. So, in this case this particular graph is for a Au2s nanoshell coated with gold. So, here the core is Au2s, that is a dielectric which is gold sulphide, and it is coated by gold. So, here is another example of a silica core which is kept fixed at 60 nanometer, and then the gold thickness or the shell thickness has been varied from 5 nanometer to 20 nanometer. So, here it is 5 nanometer, here it is 20 nanometer. You can see for 5 it is here, for 20 it is blue shifted. So, thicker the gold shell, the resonance goes back towards the actual gold nanosphere resonance. So, more thicker you will make, it will go towards 520. Okay. This is how you can remember that what happens with this thing. Okay. So, always remember it is very simple formula. So, epsilon 1 is the core permittivity. The core can be gold, or it can be or any metal, or it can be even dielectric, and epsilon 2, in this case we are considering that the core is basically dielectric, and the shell, that is epsilon 2, is having real and imaginary part, that means it is a metal. Okay. So, this formula is particularly for one case, that is dielectric core metallic shell nanoparticle. So, once again, to avoid confusion, let me reiterate, gold coated Au2s nanoshell means the core is Au2s, that is gold sulphide, which is basically a dielectric material, and it is coated with gold. That is why it is called gold coated Au2s nanoshells. Now, there are different other particles also possible. So, you can see all different shapes and sizes are possible. These are spherical, these are all rod type, different types of rods. These are like 2D polygonal type, these are 3D polyhedral type. There can be branched, there can be complex nanoparticles, then you can also have particles with hollow structures. So, all these different plasmonic structures are possible, which shows different kind of LSPR properties, and also they will have it will be difficult for anyone to calculate the resonance condition for these complex shaped particles, but for sphere and rods you will be able to approximate them using quasi-static theory and all. Remaining you have to go for different other methods. Here are some of the numerical methods that you can use. So, as I mentioned, Me theory can be used for spherical particles or infinite cylinders. You can go for transfer matrix method, where you have multiple layers and you can multiply them. These are like different types of transfer matrix method is also kind of a computational method. Okay. Discrete DDA, discrete dipole approximation, is what is shown here. So, a sphere or any other shape can be approximated with tiny dipoles, and then the response of each dipole is calculated in the presence of the incident electric field plus the electric field of the neighboring dipoles, and in this case you will be able to do approximation for any complicated shape. So, DDA method is a numerical method that allows you to do for any complicated shape, but there is a convergence criteria that mod NKD, D is the interdipole separation, that should be less than 1 for this calculation to converge. Then you have finite element method, or you can use FDTD, this is finite difference time domain method. So, there are two different approaches for calculating the scattering and absorption cross section. Always remember that FEM is a frequency domain method, where you are doing it, solving it for every frequency, whereas in time domain method you can actually do it for one time pulse that covers a broad band of frequency, and you can get the entire spectra in one go. Okay. So, these are different methods that does the same objective. Okay. Now, we studied all the single nanoparticles till now. Now, we can also look at what happens when the two particles come together. In that case, the separation between the particle also plays a very important role. So, here you can see the absorption spectrum of the dimer. Two particles is called dimer. So, when the electric field is polarized along the length of this nanoparticle axis, you see depending on the separation. So, the separation, this is 100, 40, 20, 10, 4 and 2. So, it is kind of a nonlinear interaction and it gets very stronger, and you get significant amount of redshift when the particles are very close to each other. So, what happens when the particles are very close to each other? They interact, the near field of the particles, they interact very strongly with each other, and that changes the overall plasmon resonance of this coupled system. But the same particle dimer you take, but you change the electric field direction, okay, perpendicular to the dimer axis, you will see that the change is not that significant. Okay, it only increases, or to some extent for s equal to, it even gets weaker. Okay, because you can see here the electric field is in and out of the plane, and that is how each particle is more or less behaving like single particles. Okay, the coupling between them is along this axis, but there is no electric field along this axis. So, there is no essentially any effect of coupling. So, absorption power, if you calculate the absorption power for a 50 nanometer diameter particle, so you can actually plot that, okay, with function of this gap. So, you can see the absorption power significantly increases when the separation reduces for the electric field polarized along the dimer axis. So, this is a exponential fit that you can see, P equals P naught plus A or alpha, you can say e to the power minus s over L. Okay, and the decay length is also found out, that is where the initial resonance decay up to 1 by Eth value, and this is the incident in light intensity used here. So, with this kind of scale, you will be able to measure what is the separation between the particles, because you have a kind of power law. This is a exponential decay. So, you can follow this decay pattern and you will be able to guess what is the nanoscale separation between the particles. So, these particles were assumed to be all in air, but in reality that is not the case. In reality, your particles will be placed on a substrate. Now, when a particle is placed on a substrate, there is some effect from the dielectric substrate or the metallic substrate. Let us assume that here the substrate is a dielectric substrate. Okay, I will tell you briefly what happens in metallic substrate as well. But here in dielectric substrate, when you put a particle close to each other, each charge will form a image charge. So, a positive charge will induce a negative charge will induce a positive charge. So, that way there will be a particle and there will be an image created inside the substrate. Now, if the particle and its image are very close to each other, that will only happen when the particle is placed directly on the substrate or it is placed very close to the substrate. You will see that they also start interacting with each other. Now, that also depends on the polarization direction of the incident electric field. If electric field is polarized along this direction, the coupling will be strong, that you have seen right now, because this now becomes a dimer again. But if it is along this one, that is orthogonal to the dimer axis, then the interaction will be weak. Here also you can see that when it is in air, you have more or less uniform electric field on both sides, but when you have a dielectric substrate, the field is basically confined in this near field zone. So, here also you can see that with reduction in size or gap, gap of the silver nanosphere to a dielectric substrate, you are getting much stronger resonance and there is a redshift. And this is a comparison for different size and silica substrate and gold and silver substrate, what happens. Okay. So, depending on whether it is a dielectric substrate or a metallic substrate, the image charge formation will be different. Now, there can be other complex sized nanoparticles possible. So, something like it is a gold nanorod coated with silver nanocuboid. So this kind of complex rods, complex shapes are also possible. You can write discrete dipole approximation codes to simulate the extinction property of this one. So here is the property in water and chloroform. So there is a distinct shift in the resonance property when there is change in the refractive index. So that is what you can expect, that this nanoparticles resonance is very much dependent on the surrounding permittivity. So they all can actually act as a refractive index sensor. One more other thing is that you can also do a thorough analysis of these different peak positions. You see there are 4 different peaks. So when you see these peak positions, you can see that what is basically creating these peaks. So simulation helps you to understand this, because in real life when these nanoparticles are dispersed in solution, some of them may be in this way, some of them may be in this way. So there is a possibility of you to excite the longitudinal mode or the transverse mode. So transverse mode can be in 2 ways, it can be in this direction or this direction, but the longitudinal mode is along the length. Fine. Now simulation allows you to see that this particular mode is basically coming from the longitudinal. LE means longitudinal edge excitation, and other 3 modes are basically coming from the transverse excitation, and when you add them up you will get this one. So unpolarized light can be assumed to be a combination of this polarization plus this polarization, or you can take a weighted average of it, because there are two cases of transverse polarization. So you can make it like LE plus 2 TE by 3, then you can get this kind of a graph. So this graph reproduces this one, so that is perfectly fine. And if you look into the electric field distribution at 4, this is the case. So this is the longitudinal dipole, this one, this is for the 3, peak number 3, this is a transverse dipole. Okay. Then you are also able to see these are octopolar modes, type 1 and type 2. Okay. Now quadrupolar mode you will not be able to see, because that is basically a dark mode that can only be seen in the absorption spectrum, okay, not in the scattering spectrum. Now so these nanoparticles plasmon resonance are also highly tunable depending on different shell. So here there are 2 types of shell thickness. One is side shell thickness, LS. So when you change LS, this is how you can change the resonance peak positions, and you can also change LE, that is the edge shell thickness. So you see the overall LS has got much stronger effect than LE, because this actually changes the aspect ratio of the overall structure much significantly than this one, because it is already a longitudinal structure. Now what to do with this kind of nanoparticles, and why do we learn this? Because if you make a 2D array of nanosheets that we have seen in the previous lecture also, in this case let us assume that we are taking a silver nanocuboid, and it is basically fabricated using a gold seed at the center. So you start with a gold nanoparticle seed, and then you start depositing silver on top of that, and with time more and more silver gets deposited and you get a cubic shape. So in this case the LSS side to side separation and edge to edge separation are same, and when you measure it in a experimental spectrum, so these are the actual distribution. So here you see the main gap is around 10 nanometer, right. So you can also use a Gaussian kind of distribution to it, and you can simulate this kind of nanosheets extinction spectrum through simulation, and you will get a very similar kind of a resonance characteristics. This simulation can be done using DDS-CAT, or you can use COMSOL or CST, any other software numerical simulation tool. Okay. Now why it is important? Because this kind of large 2D array of plasmonic nanoantennas can give rise to free surface propagating modes. Just like graphene has got abundance of surface plasmon propagating on top of it when you can excite it. This also gives you this kind of surface plasmon propagation on the top of the surface of this closely packed, you can say, plasmonic nano antenna array. So, it is like a sheet. So, this is a sheet of this nice packing of nano antennas, and you can get this propagating plasmon modes. You can also cut these sheets in form of waveguides, and you can find surface plasmon propagation along the edges and along the center of the nanoribbon. So, these are plasmine nanoribbon and plasmine nanosheet. Okay. Now, why these are important? Because these plasmine nanosheets, as you can see, they have so many so much of region around these nanoparticles which are having very strong local field concentration. So, if you use that for surface enhanced Raman scattering, you should be able to sense very tiny amount of molecule. Okay. Now, coming back to what is surface enhanced Raman scattering, you remember the power of Stokes scattered beam. So, this is Rayleigh scattering, the same energy comes back. Okay. This is Stokes scattering. So, you jump from here 0th state to the virtual high state, and when you come back, you do not come back to the 0 state, you come back to a higher energy state. So, there is a difference in the energy. So, this is called Stokes Raman scattering. The other case is also possible that you actually jump to the higher state from not 0th state of the ground level, or you can actually start from first state, but while you come back to the 0. So, you are releasing more energy while coming. Okay. So, these are different vibrational energy state, and this particular case is called a anti-Stokes Raman scattering. So, the power of the Stokes, so if you look into the Stokes scattering, that is the most common one. So, in that case, Ps omega s is proportional to, or you can say is equal to, n sigma rs and intensity. N is the number of Stokes active scatterers, sigma rs is the scattering cross section of that atoms or molecules, and I is the intensity of the excitation beam. Now, when you do this experiment or you do this probing of the molecule in the presence of a metallic nanostructure, near the nanostructures, the Raman intensity, this scattering Raman scattering intensity increases dramatically, and that happens in because of two things. One is the increase in Raman cross section due to change in environment of the molecule, that is you can get up to like 10 to the power 2 order of enhancement, because the particles that scatterer surrounding media now has a metallic particle. Okay, so the surrounding environment has changed, and the second thing is coming from the increased electromagnetic field due to localized surface plasmon resonance. Now, that plays a very important role. So, now this is the normal case when no nanoparticle is there, but this is the case when nanoparticle is present. You can see that two new terms got added up. What is L omega, this one L omega excitation square, okay, and L omega s square. What is this L? L is basically the enhancement factor, which is E loc over E naught. What is E local? There is a localized electric field over the incident electric field. So, you are able to get very strong enhancement, and because of this two cases, that Raman scattering is maximum when the excitation also matches with the scatterer frequency. So, these two terms can be combined and you will get it to the power of 4. So, the enhancement that happens because of LSPR to the SERS is basically E local by E naught to the power 4. So, that is how it affects. So, now you can see the importance of this plasmine sheet, that if you take this plasmine sheet and have electric field polarized along this axis, you will feel all these hot spots. So, you can do sensing very tiny, even femtomolar amount of molecules or atoms can be sensed. Similarly, when you have the electric field along this direction, vertical direction, you actually form the hotspots in the vertical direction, and in a case of unpolarized light, you can actually have electric field mainly concentrated at the corners of the nanosheet. Okay. So, they all can be used for sensing. So, enhancement factor is basically dependent on the enhancement of electric field to the power 4. So, that is how these nanosheets are important. These are also scalable. So, you can work with a small area or large area, you will get similar effect. There are different effects of size and shape of the nanoparticles participating in this LSPR. So, you can think of this kind of a structure. Okay. So, these are analog to say liquid crystals. So, when they are forming a horizontal sheet, they have a resonance around 842, but when these nanoparticles are all standing up, they form a vertical sheet. So, you will get a 555 nanometer wavelength. So, what you see here is that for this kind of vertical sheet, only at laser wavelength which is close to its resonance, you get the strongest electric field. For other cases, the electric field in the near vicinity of the particle is not that strong. Similarly, for the horizontal sheet, the resonance is at 842. So, only when the probing laser is close to that resonance wavelength, you get the strongest hotspots in between the particles. Other cases, these are not that strong. So, always remember, for most effective SERS based sensing, the LSPR of the nanoparticle must be as close as possible to the excitation laser wavelength. Next important application for LSPR is the enhancement in fluorescence. Now, what is fluorescence? If you look into Wikipedia for the definition of fluorescence, it is basically a two-stage chemical process that involves absorption of a shorter wavelength or higher energy light by a chemical fluorophore, which is basically a protein or a carotenoid, and followed by the release of some of the absorbed energy as longer wavelength. Longer wavelength means shorter energy. So, this is where it is giving down shorter energy. So, this is called fluorescence. Now, again, the excitation of surface plasmon resonance in nanoparticles result in nanoscale confinement of electromagnetic field near the metallic surface, and that could significantly enhance the density or local density of optical states. So, that will also allow you to improve the fluorescence effect. So, such properties are widely employed to study the interaction between plasmons and fluorophores, such as fluorescence enhancement and the realization of plasmonic nanolaser. So, in plasmon enhanced fluorescence, there are two kinds of important mechanism, or you can say enhancement mechanism. One is excitation enhancement, another is emission enhancement. So, how it works? You can see here that the ever essence of this phenomena is that the excitation emission efficiency eta of the fluorescence molecule is related simultaneously to the excitation efficiency, which is gamma Ex, and the emission efficiency, which is gamma Em. So, eta can be written as gamma Ex times gamma Em. Now, what is gamma Ex? Gamma Ex basically is the ratio of the electric field intensity of the total field over the incident field in the position of the fluorophore. And what is gamma Em? That is basically the scattering cross section, ratio of scattering cross section in the presence and absence of the metallic nanoparticle. So, that way you are able to boost up this particular eta by boosting both these two. So, there is one particular example in this paper where they have used a gold nanorod, and they have used the excitation, the transverse excitation to match with the excitation wavelength. So that is where they got one resonance, and they have also got the longitudinal surface plasmon resonance to match the emission wavelength. So this is how they were able to boost up both, and that has dramatically boosted the efficiency of fluorescence. So that is eta was boosted by double impact on excitation efficiency as well as emission efficiency. Prior to this paper, what people used to do, people used to either boost up this one using 1 nanoparticle LSPR, or either this one, or worst case to get a compromised, not worst case I should say, to get a compromised optimum, they used to choose a LSPR which is in the middle of these two wavelengths. Okay, but in this particular paper they found a way to excite both from the same particle, because they were able to excite, when you put unpolarized light on this particle, both this and this will be excited, right? Because transverse and longitudinal, both plasmons will be excited, so you will get boost in both these two efficiencies. So that was one very good example of using nanoparticles for fluorescence enhancement. Next we move on to some examples of using nanoparticles or LSPR in electrotunable Fabry-Perot interferometer. Now what is a Fabry-Perot interferometer? You must have known this. This is basically a cavity formed between two mirrors. There is a dielectric media in between, which is having a permittivity of N, and this is the length L of the cavity. So when some light enters this cavity, it goes through multiple reflections, and only those wavelength which satisfies the constructive interference condition, that is the round trip phase should be integral multiple of 2 pi. They are able to come out of this. Other wavelengths will get cancelled. So you actually send a broadband light, you will get a single narrow transmission peak. So this is how Fabry-Perot interferometer can be used as a selective transmission filter. Now how do you change the transmission wavelength? Either you have to mechanically adjust the length of this cavity, or you have to physically change the cavity medium N. Then this particular transmission wavelength will change. Now nanoparticle based solutions or plasmonic nanoparticle solutions allow you to achieve a electrotunable Fabry-Perot interferometer cavity. So what you can do, I will quickly go to the structure. So you can use two metallic electrodes, transparent metallic electrodes like ITO, and you can use a aqueous solution or water solution filled with gold nanoparticles which are having negatively charged. They are having some kind of ligands associated which keep them negatively charged. Now when your electrodes are negatively charged, nanoparticles are also negatively charged, they repel each other. So nanoparticles will be in the solution in the cavity itself, but light can simply enter and reflect, some part will get absorbed. But as soon as you make the electrodes positively charged, what will happen? This negative nanoparticles, negatively charged nanoparticles will come and assemble on top of this electrodes, and they will start forming a array, 2D array. And as they keep on getting denser and denser, the reflectivity of the 2D array will get stronger. And that is the reason why I have shown those kind of 2D assembly. So here also you are able to pack a very dense assembly of particles, 2D sheet of particles, and they form like mirrors. So these are basically electrically tunable mirrors, and using this you can change what should be the transmission wavelength. So one thing I forgot to mention here is that other than this one and this one, the third method is to change the reflectivity R1 and R2 of the Fabry-Perot interferometer. So in this particular case, we are using nanoparticles to change R1 and R2 of the mirrors. Okay, that also allows you to change the reflectivity. So this is the transmittance formula T when absorption in the cavity is non-zero. So you have 1 over 1 plus capital F sine square delta by 2. What is K? K k square, 1 minus A is the absorption, and R square minus 1 minus R square. R is basically the reflection coefficient of this mirrors. We are taking identical mirrors, okay, and capital F is the coefficient of thinness that can be calculated like this, okay. So what is important here to see that by changing the voltage you are able to bring more nanoparticles, and that will allow you to build a mirror with tunable reflectivity. So this is one of my research work which has been published long back, and with that I will show you some of the results. So here the delta, which is the round trip phase difference, okay, that also can be seen is basically a function of R. So by changing R you are able to change this one as well. So when you compare this with here, you see this is the plot of the transmittance for a specific lambda. So I am taking 800 nanometer. Nanoparticle size is chosen to be 20 nanometer. These are gold nanoparticles, and A is the lattice spacing, which is 2R plus A, that is the gap. 2R is the diameter plus A, 4R, 4 is the gap between this particle, surface to surface gap, okay. So when you do this, okay, you are able to match the effective medium theory calculations with classical Fabry-Perot interferometer cavity, and you are able to see that you are getting peak transmittance at integral multiple of pi. So at p pi, p plus 1 pi, p plus 2 pi, or p minus 1 pi, you are able to get the transmittance. So these are the cases where your phase, round trip phase is getting integral multiple of 2 pi, okay. So these are, look at B. So here what is the difference? Here lambda is same, the particle radius is same, but the gap between the particles are changing. So gap between the particles changing means what? The coupling between the particles will change. So the overall reflectivity of that surface that is created by this array of particles will also change. So here you can see this is for G equals 30, means the gap between the particles is 30, then 20, 16, 12, 8 and 4. So as you can see, when it is 4 means the particles are very close to each other, you can see very strong effect of this resonance, Fabry-Perot interferometer cavity resonance, and that is how you get a very high quality factor. But as you keep on increasing the gap between the particles, the mirrors are becoming weaker, okay, mirror reflectivity is getting down, so your cavity quality factor is also coming down. But this does not actually show you the wavelength tunability yet. Let me show you that as well. So here you get G equals 4, G equals 8. So this is the wavelength tunability. Here you can see the cavity length is fixed, nanoparticle size is fixed, okay, cavity length is 1000 nanometer, that is 1 micron, okay. So you can change the nanoparticle sizes from 4, gap between the nanoparticles from 4 nanometer to 8 nanometer. You can see you are able to move from here to here. You can also see a linear scaling like 2, 3, 4, 5, 6. This is the way you change the gap. So you are also able to continuously tune the transmittance peak, okay. Though the peak transmittance value also reduces, because that is a kind of price you will pay with this particular cavity, because when the mirror quality comes down, okay, so the quality factor also gets affected as we have seen here, but the wavelength selectivity or wavelength tunability is continuous with this particular different gaps. So how you can change? You can change the potential on the electrodes, and that will give you electrically tunable Fabry-Perot interferometer cavity. So these are just examples of 1 or 2 tunable optical devices that we can make using this. So if you are interested in much more of this kind of electrically tunable LSPR based devices or their applications, you want to know more, you can always discuss with me by dropping an email to this particular email address. So here we will stop. Thank you.